Check this one out. There's a wire along the x-axis that carries current I in the negative x direction through the magnetic field B. B varies, as you can see, with x. Draw a graph of B versus x over this interval and find an expression of the net force on the wire. Find also an expression for the net torque on the wire if you put the pivot point at x equals 0. I mean, that in itself, this seems like a pretty involved problem. Okay, so they need a graph. Sure thing. What are we drawing? From 0 to 1, we exist. We don't exist anywhere else. Well, easy problem for me. That means I can do this kind of plot. And that's the magnetic field versus x. So you only exist between, again, 0 and 1. What function are you following? It seems like it's a linear function, and the slope is b naught over L right now. So, okay, positive slope then, it's going up. I don't know how big b naught over L is, but I can only assume that it will go up at some rate. So here's the magnetic field, essentially. And then you get 0. You know, both before and after here. Maybe I should have added a little bit of a negative axis. Too late now, I guess. There we go. So we get 0 for the rest of time. So this is very interesting as a function, I mean, because it's discontinuous, and yeah, it's definitely going to cause trouble because of that. All right, so that's a good picture here to have for our magnetic field as a function of x. Now, what are we going to do with the wire? So it says that the direction is k hat, but the wire has a current. It's on the x-axis. So in a way, you have the wire over here. Let's symbolize it in blue, like that. This is the x-axis, let's say. Give it again a little bit of an extent here, like that. The k hat direction would be out of the page right now if you do this diagram, and the axis is x and y. So it looks to me, guys, if we were to draw this properly, you can see that the field only exists from 0 to 1. I'm going to try and align these plots so you can understand what's going on. I think that the wire is infinite. Okay, I'm pretty sure that it's infinite, so it never ends. But it runs the current in the negative x direction. So this way. The magnetic field doesn't exist in this region here, but it does exist over here until 1, of course. And it seems to be growing in strength as you go from 0 to 1. So, okay, let me indicate it again since it's in the k direction. It's going to be really small near the origin. It's coming out of the page. Let's make some copies. Okay, so really small here, tiny, like it's going to 0. And then it's growing more, right? And more, and more. To the point where it comes to a maximum at 1. But then it goes back to 0. So that's what's interesting about this. All right, nothing beyond 1. Might as well just write here b is equal to 0. All right, that's good. You have a picture now of how it looks like. It's going to help a lot. So the magnetic field right now will provide a force along, again, each of the pieces here of this wire. I can choose over here, folks, to pick like a little segment DL, like right there. arbitrary, and the DL always has the direction of the current. So it goes to the left. What the heck is this DL? Well, it's a small step in the x direction. Let's start from that. So it's a small step in the x, and it's directed in the negative x. So that will be its direction then. Well, that's out of the way. Now, what else do we need here? I have the current, and I have the magnetic field. So it's time to go and do some calculations. It asks here, draw a graph of b versus x over the interval -3 over 2l x 3 halves. Why specifically these guys, though? I don't understand why that specificity. I guess you're plotting it. My plot is better. It includes this and more, so I'm just gonna keep it as it was. I guess 3/4 of L, eh? So if x goes from 0 to 1, we exist. If this is 1, then you're gonna get B naught over L. That's all we know. Okay, so L is arbitrary here. Hasn't been specified. I have no idea if it refers to length of the wire, but the wire seems to be infinite, according to the surrounding text. So I don't think this has to do anything with the wire. It's like a parameter of some, like a scaling parameter. Anyways, the B here says find an expression for the net force on the wire. It makes sense probably to you to understand here what I'm about to do. I want to calculate the force on a little segment of that wire right now. You see, I can go over here and pick that DL, of course. Let me get that back in. So pick a random DL and then take the magnetic field and apply it there. As you can see, the DL with the magnetic field they're mutually perpendicular no matter where I am on the wire, because the DL points to the left all the time, but the B points out of the page all the time. So, they are mutually perpendicular. So, at the end of the day, if you do the right-hand rule and talk about the force that this segment feels, it will be the cross product between the length element dl. Let me write it carefully here. Put the current down, I. Put the length element dl and cross it with a magnetic field. Okay, so this will give you the differential force that this segment is feeling.
Hey, just curious, could we have a problem like this where we have to find the differential force, but instead of the length changing its current? So it would be like di times L times B?
Well, let me ask you this. This together, surprise, that's the I. Actually, we separate usually the magnitude of di with its direction. At any given time, dl plays the role of the direction of this vector, and I plays the magnitude of it.
Okay.
So, yeah, di as a vector has magnitude I, and if we slap on it the dl, we give it direction. I know what you're gonna say, and you'd raise very good questions if you asked me, how the heck is the di equal to I? Isn't this supposed to be smaller than I? No. Anywhere you touch over here and you draw a cross section, you experience the same amount of current coming through. Okay, when you dissect the wire and ask how many electrons are coming through per unit time, you always experience I. I is a flow rate. So no matter where you dissect the wire, okay, right here, anywhere, you're going to feel I going through. So that size is di. There are other problems in E&M where that's not true. Obviously, if I have a surface current, right, and I have a surface current density K, and I want to find how much current goes through this cross section here, dl, then all I have to do to find the di is actually integrate this current density across the surface. Yes, there are times where that's not true, but in an infinitely thin wire, the current is the size of di. Okay, there are no other portions that I'm missing. When I'm measuring the current here, there are no other portions of I that I'm missing. I'm seeing the full current at once. But over here, if I take a portion of the object, if I take a little portion of it, I don't see the full current. I'd have to take the entire plane to see the full current, right? That's going through that. Here, if you take a little point, the entire current goes through it. Very different from this one, where you have to integrate the entire opening here. So basically what I'm trying to say, if you want to think about a wire, think about a plane like this, squashed. You can see that the opening now is a point, and all the vectors go through it. So it's I at the end of the day. Anyways, good interjection there, but that is indeed di that we wrote over here. We like to see it in this way, though, IDL. It's more useful as a form. So what do you do next? Well, take your right-hand rule. Line up your thumb with DL, so to the left, and then point your finger to yourself. Your middle finger should be opening up. It's hard to do because you have to crimp your hand a little bit. So thumb on the left, index finger to yourself, and then the middle finger should be opening up. This will be DFB. Okay. So you found what DFB is. Okay. Now I have to put it all down. Let's see what happens. So DFB is IDL crossed with B. Here we go. The next piece of info I would put down is what the DL element is, which we found it to be, if you remember, dx negative x hat. And then we have the magnetic field. So the magnetic field I will address in a second. All right. So at the end of the day, we have to integrate that DFB to get the total force, of course, that's acting on the wire. Duh. So I have to integrate the right-hand side. It seems right now like I have a negative x hat. I can pull the negative outside. And then the I is also constant. So inside I would have simply the x hat with dx, I guess, crossed with the magnetic field. Follow me closely here. Crossed again with the magnetic field. But you see the magnetic field, sorry, I need to be careful here. This integral, guys, would take place from negative infinity to infinity, by the way, since the wire is infinite. But there's a catch. The magnetic field for certain intervals is gone. For example, from here to here, you don't have a magnetic field. You remember, it's 0 before 0. Then you continue the integral from 0 to 1, I guess. And now the magnetic field becomes something. So you have dx x hat crossed with the magnetic field. And they told us that in that interval, it is B naught over L times X, and the direction of it was in the Z hat. That's what you get for that term. And then, of course, if you're beyond the 1, so if you continue from 1 to infinity, then again, you get nothing. See, so it's not as big of an integral as you guys thought it would be. It's just in that region that the magnetic field exists. So that's gone. That's gone. Okay. And you only have the middle guy. The negative I is factored from all of these. So you can put a little bracket here. All right. So at the end of the day, I do want to make this, give it a little more space. So at the end of the day, you have to do this integral. Doing the cross product, we will use a right-hand rule again. We have negative I, pull out the constants, B naught over L, and then you have x dx from 0 to 1, and then you're crossing x hat with z hat. That's what's left to do. It's not hard. Thumb along x, okay? Index toward yourselves. I mean, we already did that. It's positive y. We already proved it, that it goes up. So no surprises there. That's going to be just y hat. And from there, you do said integral. I just want to be a little careful, though, with a negative there. Oh, I see. Wait a minute. Thumb was going to the left. B was going out. No, that is correct. You're going to get it to go up. Oh, I see. But if you don't include the negative and you do x hat, I see what I did wrong. If you do x hat crossed with z, you're going to get actually negative y. And the negative with a negative will cancel and get you the positive y. Okay, I was tripping a little bit. So that it's a double negative there canceling, basically. And the integral is just x squared over 2 from 0 to 1. You understand that that's just going to be 1/2. And that's the end of the story. That is the net force on the wire. There you go. Oof. So set up the differential. This is Lorentz force for wires. Okay.
George, I wanted to let you know the bounds is not 0 to 1; it's 0 to L. It got me earlier too when I was doing this.
No way, you're kidding.
Because yeah, it's the same as like how it is in the interval. Look at the interval. It's yeah. So I think it's 0 to L.
My God, they knew
It's
knew
not
this was gonna happen.
Just,
Yeah, they knew this was gonna happen, and they still did it anyways. Yeah, it's not a big change. It's just annoying. All right, I'll just correct it here quickly.
Like yeah, the exact same thing got me earlier as well.
Yeah, thanks for letting me know, because that's definitely a hard one to spot.
Mm-hmm.
All right, IB naught over 2, and then that's your net force. And if you add the vector sign, of course, you have it to go in the y hat. The negatives have canceled. Done and done. As for torque, because torque is a little bit trickier, you have to set a pivot point to measure it. So this is A, this is B. And I know that you guys all probably despise torque. It says find an expression for the net torque on the wire about the point x equals 0. So bring back the plot that we had over here. I'm going to recycle it a little bit and show you what's going to happen here. I want you to understand that when I'm doing torque this time, I care about summing the infinitesimal torques, I guess, that are acting on this wire. I am supposed to be taking the pivot or the rotation axis to be right there. Now, conveniently, if I pivot the wire there, I don't have to worry about any forces here, only about forces here. I want you to see that each of these DLs is going to contribute some sizable force. It's actually going to go up as you're going toward the bound. Because again, the magnetic field is increasing, right? So that's what you have over here, the picture at least. That's how it looks like. You see what I mean? It's like vectors that are increasing in size as you get to the bound. And each one of these provides a torque, as you can see. So it remains now for me to do the following. I know what DL is, and I know that basically it's an infinitesimal little guy here. Okay, that's sitting on our wire like this. And the current produces this kind of force. Now, with respect to the rotation axis, I can open up a vector. Okay, it's called the R vector here. Conveniently, this R vector will be the moment arm because it intercepts all of these force vectors perpendicularly, as you can see. Very convenient because all of these force vectors are perpendicular. What is a good variable to give the size of R? You might be wondering, because every vector has a size and a direction. The direction is definitely x hat. And as you can imagine, since it measures distance with respect to the y-axis, a good variable for its size would be x. Right? X would keep track of where you are right here, you know? Just keep x to describe its size. Easy. This guy, out of the way. So that's R. And then I have to calculate the little torque that I get from this little guy right here. I'm going to experience some torque right now. From all these acting here at this small DL. And I'm going to call it d tau for the time being. What is d tau? Well, it's going to be, quite obviously here, the R vector that you just figured out crossed with a force F. That's by definition of what torque is, by the way. R crossed with F, but here we're doing infinitesimals, so it's going to be d tau and df here. Seems legit, so I'm going to go over there. I'm going to put in what R vector is, which is x hat, and I'm going to put what the dfb is, which is going to be, I had it here, this guy. There you go. Beautiful. So you got to be careful because you're crossing these. I suppose you could write the DFB as a piecewise function. Before I get to this stage, I can say that DFB would be the following. It would be 0, of course, if the values of x are less than 0 or greater than L. And this DFB we found earlier, what will it be if we're not 0? It's going to be this guy right here. But we can simplify that very, very much. So again, the DFB would be the current, the direction of DL, crossed with B, where the DL again, just going to summarize here, the DL was negative dx x hat, and the B was B naught over L x z hat. And when we did this cross product with everybody again considered here, we got I dx B naught over L x X hat with Z hat, we gave negative Y hat, but then we have another negative there. So it became a positive Y hat. And that's what we get for DFB. So I'm just summarizing all of that here. Boom. I don't have to redo it because I've done it in the previous problem. And this DFB is valid for values of X between 0 and L. Inclusive. There you go. So, all looks great. I might shuffle this a little bit because it looks disgusting the way I've written it. I B naught maybe over L here. And then dx, or x rather, dx y hat. That's much better. So this is waiting again to be cross-producted. No problemo. We're going to cross-product it here with DFB. So you're cross-producting it basically with this, because the other result's going to give you 0. All right, folks. What do we get? We end up with x squared, IB naught over L. All right. And then the cross product between x hat and y hat. And then dx. Very nice. So, of course, if you put your thumb along x and your index along y, the middle finger should point toward your face. That means that we're getting z hat for this torque. Okay. Remember, this is still d tau. I gotta find what tau is. So this is the moment that we switch into an integral right after. Tau is, okay, I B naught over L, the integral of x squared z hat dx, and for however long this is valid, right? From 0 to L. Boom, boom. Oops. All right, so you walk over there, you get the result. It's going to be the total torque IB naught over L. L cubed, that's what you're going to get from the integral, over 3. And that is the last answer. That's the torque. About x equals 0. What do you guys think? Good problem?
Yeah.
Yeah, pretty interesting stuff, right? You have to find the unit torque element here from one of these DFBs, and then you want to integrate it across the extent of the, well, however much you're feeling force for. You're feeling force until you get to L on this diagram. From 0 to L. And then nothing. Okay, so you are going to be turned this way, and the strength is going to be IB naught L squared over 3. Questions? All right, I will assume nothing. Okay, I'll close the recording of that one here.